Under 1 pound is the total weight of a specialized fishing rod that manages to restrain marine animals weighing hundreds of pounds. Why can such a lightweight instrument withstand the immense pressure of a deep-sea predator? It only looks obvious that a rod is a simple, flexible stick, but in reality, this structural integrity is the result of rigorous engineering within the production facility. Every individual layer of composite material and the specific angle of every fiber is calculated to govern how the tool distributes tension. The process is only gaining momentum. One can notice how technicians prepare the foundational mandrel, which serves as the precise internal mold for the future rod. The equipment gradually applies pre-impregnated carbon fiber sheets onto this steel core with constant mechanical tension. This stage is critical because the orientation of the fibers determines whether the rod will possess longitudinal strength or torsional rigidity. But this is just the beginning. It seems simple to wrap layers of fabric, but in reality, any air pocket or misalignment would lead to a catastrophic failure under the weight of a heavy catch. The manufacturing sequence moves to the next level of complexity as the wrapped blanks are tightly bound in heat-shrunk tape. One can notice the machine rotating the mandrel at a steady speed to ensure the compression is perfectly uniform across the entire length. This pressure is essential to force out excess resin and consolidate the layers into a single monolithic structure. Everything only gets more complicated as the rods are moved into specialized industrial ovens. 300 degrees or higher is the temperature maintained during the curing cycle to trigger the chemical hardening of the resin. The camera glides along the racks of rods as they undergo this thermal transformation for several hours. This heat treatment converts the soft, pliable sheets into a high-strength composite that responds to the slightest movement of an angler. The material is ready to move to the next processing phase without haste. $1,800 million is the annual revenue generated by the global fishing rod market, a figure that highlights the immense scale of this industrial sector. Why does a tool that appears so structurally simple require such a massive production infrastructure? It only looks obvious that a slender rod is a basic implement for recreation, but in reality, it is the product of a complex manufacturing chain that operates without interruption across the entire planet. This high-volume industry serves a diverse range of users, from casual recreational anglers to the elite participants of professional sport fishing competitions. More than 100 million fishing rods are manufactured and circulated throughout the world every single year. Major demand for these products is concentrated in specific geographic markets, most notably the United States, Europe, and Australia. One can notice how the equipment gradually evolved from natural materials to advanced composites. At first glance, many people still assume that modern rods are constructed from traditional bamboo. But this is just the beginning of the technical transformation. In reality, the majority of contemporary fishing rods are built from carbon fiber, a high-performance material originally developed for the demanding requirements of the aerospace industry. It seems simple to use a modern composite, but the true distinction of a high-quality rod lies in its internal architecture. The process is only gaining momentum as the camera glides along the production line where robotic systems and human technicians interact. What truly sets these tools apart is not the raw material alone, but the meticulous way each structural layer is arranged and controlled during assembly. Every individual fiber is placed with a degree of precision that is measured down to fractions of an inch. Transition to the next level of the process reveals how this layered construction ensures the necessary strength and flexibility. The manufacturing sequence concludes this phase by preparing the composite blanks for the intense stress of the water. Two primary materials serve as the foundation for the rod blank: carbon fiber pre-preg and fiberglass pre-preg, both consisting of fibers previously impregnated with a heat-reactive resin. Why must these materials be handled with such extreme temporal precision? It would seem that the resin acts as a simple bonding agent, but in reality, it is a volatile chemical component designed to harden only when exposed to specific high temperatures. If the pre-preg remains in normal ambient conditions for an extended duration, it can begin curing prematurely and transform into unusable waste. Because of this sensitivity, all pre-preg materials are stored in specialized cold rooms at temperatures below 32 degrees Fahrenheit. The equipment is only removed from these climate-controlled environments at the exact moment it is needed for the production line. As soon as the material exits cold storage, a critical countdown begins to ensure the resin remains viable. One can notice how the material is unrolled and laid perfectly flat onto the cutting table, strictly following every technical outline provided by the engineering team. The process is only gaining momentum. A technician performs hand measurements to carefully align the edges of the material, and then the machine executes each pre-programmed cutting pattern with controlled precision. To maintain high productivity, each cutting cycle processes between 8 and 10 layers of carbon at the same time. Accuracy must still be preserved down to fractions of an inch, as the equipment gradually slices through the dense fiber stacks. It only looks obvious that a straight cut would be sufficient, but in reality, carbon is rarely cut in linear paths. Instead, the material is shaped into specific triangular forms or complex diagonal patterns. This precise cutting geometry controls exactly how force travels along the length of the finished rod when it eventually bends under a heavy load. It gets more complex further on. A single piece cut off by just a small fraction of an inch can shift the entire flex point of the rod, ruining its mechanical properties. One can see how the blades move with millisecond accuracy to avoid any deviation in the fiber orientation. This concludes the preparation of the fundamental components for the rod structure. 100% precision is required as the material is positioned onto the mandrel, a specialized stainless steel shaft that acts as the internal forming mold. This steel core is typically coated with a non-stick release agent, ensuring the finished blank can be separated cleanly without surface damage after the heating cycle. Once a uniform layer of adhesive is applied along the metal surface, the technician utilizes a small heated iron to hot tack the initial layer of carbon fiber into place. Why is this first placement conducted with such manual intensity? It only looks obvious to align a sheet of material, but in reality, if the first layer deviates from the center line by even a fraction, every subsequent wrap will inherit that misalignment. Because no robots or laser guides are utilized at this stage, the structural integrity of the rod depends entirely on the technician's trained eye. The process is only gaining momentum as the mandrel is placed onto the rolling table. One can notice how the machine rotates at a slow, controlled speed, while the craftsman manually manages the wrapping of each carbon fiber layer. The technician dictates every variable, from the specific rotation speed and hand pressure to the exact moment the next layer of material is introduced. As the core turns, the fiber layers tighten against one another, closing the material edges as the rod gradually lengthens and tapers according to a calculated geometry. But this is just the beginning. Reinforcement layers are added at high stress zones, particularly near the handle, to fine-tune the tactile response of the rod during use. 3 types of specialized tape, nylon, cellophane, or vinyl, are used to bind the entire blank before it enters the thermal processing phase. The mandrel is mounted onto a wrapping machine that applies this heat-resistant tape in a continuous overlapping spiral under consistent pressure. This step locks the rod's shape in place, pressing every carbon layer firmly together to ensure a uniform wall thickness. It gets more complex further on. At this stage, the mandrel serves as the internal mold, while the tightly wound tape functions as the external mold, stabilizing the structure for curing. 284 degrees Fahrenheit is the standard temperature to which the curing ovens are heated. The mandrels carrying the rod blanks are hung onto racks and moved into the chamber, where computer systems regulate the thermal rise to prevent fluctuations. The curing phase lasts for exactly 2 hours, allowing the heat-reactive resin to fully activate and spread between the carbon fiber layers. One can notice how the separate plies merge into a nearly monolithic structure as the resin bonds the components together. After the thermal cycle is complete, any prior deviation in the alignment becomes a permanent part of the internal structure. Transition to the next level occurs as the cooling rod blank moves to the mandrel extraction stage. The blank is secured in a dedicated separation machine where a pneumatic pulling arm applies a steady, powerful force to draw the steel core out. This force must be strong enough to overcome friction, yet smooth enough to avoid deforming the newly cured carbon. If the previous heating stages were executed correctly, the mandrel slides out cleanly to leave a hollow rod blank. The technician then performs a quick inspection for straightness, relying on tactile feedback and years of experience. The process does not end at this stage, as the outer wrapping tape is peeled away in its original spiral direction. As the tape comes away, the blank is revealed with small ridges and a rough surface formed during the compression process. The material then moves to the cutting station, where a rotating blade removes excess material from both ends to reach the exact standard length. At first glance, the surface looks finished, but in reality, it must undergo both dry and wet sanding. Water is used during the final sanding stage to reduce friction and carry away resin dust while allowing for finer control over the surface texture. 0.04 of an inch is the maximum allowable deviation at the joint, where the tip and butt sections meet. The technician inserts the sections together, gently twisting and shaking the assembly to ensure there is no looseness or play. Any gap at this point would disrupt the continuity of force transfer through the rod. Once the fit is approved, the sections are grouped into bundles by model and sent to the painting workshop. Everything only gets more complicated as the base primer is applied to unify the surface for the subsequent color layers. Fluorescent paints are commonly applied to improve visibility in low light conditions over the water. The process concludes with a clear urethane top coat, which is sprayed or wiped on to provide a smooth finish resistant to ultraviolet exposure and salt water. The rod is then moved to a drying room to allow the coating to stabilize before handle assembly begins. Each component, from the EVA foam or cork handle to the reel seat, is installed by hand using specialized adhesives. One can notice how the reel seat is aligned perfectly along the central axis to ensure comfort and balance under load. Guide installation requires the technician to mark each position along the blank according to a specific design layout. Each guide is placed by eye and secured by wrapping thread tightly around the foot of the guide. The craftsman must ensure that every wrap sits cleanly beside the next without gaps or overlaps. After the guides are secured, a brush is used to apply a base layer of epoxy over each thread wrap. The rod is then placed onto a rotating rack, allowing the epoxy to level itself evenly as it passes through a curing chamber. The final assembly concludes as the tip and butt sections are joined for the first time for a comprehensive inspection. The technician rotates the rod slowly on an inspection table, observing the axial straightness with the naked eye. A flex test is performed under a controlled load to verify the structural stability and balance of the entire length. Finally, the rod is wiped down to remove all residues and examined under strong lighting for minor imperfections. The material is ready to move to the next processing phase without haste. 100% of the sensory feedback felt by an angler holding a finished fishing rod is a direct manifestation of structural consistency. Why does the material respond with such predictable precision to every external force? At first glance, the rod appears to be a simple, flexible tool, but in reality, every vibration transmitted back to the palm is the product of hundreds of technical decisions engineered deep within the factory walls. This reliability determines whether the equipment can be trusted during the intense physical stresses of real-world use. The process of ensuring this uniform response is only gaining momentum during the final assembly stages. One can notice how the rod blank reacts to a light tap, sending a ripple through the composite layers that remains undistorted from tip to handle. This behavior is not accidental. Engineers calibrate the wall thickness and resin distribution of the carbon fibers with jewelry-like precision down to the millimeter. It is visible how the structural integrity of the rod allows it to return to its original position without any residual oscillation. But this is just the beginning of the verification process, because any deviation in the alignment of the internal fibers would result in a dead spot. Sensors monitor the resonance of the blank during quality control testing. Therefore, every individual unit undergoes a rigorous mechanical evaluation to ensure it matches the master specification. The equipment gradually applies load to the tip, demonstrating a smooth curve that follows the calculated taper of the mandrel. Everything only gets more complicated when the final coatings are applied to protect the sensitive core. The consistency of the rod remains the primary factor in its performance, bridging the gap between industrial manufacturing and the tactile experience of the end user. Thus, the product reaches the standard required for its purpose, completing this phase of the technical journey.